This is the F-22 Raptor. At $143 million per aircraft, it costs more than any fighter the U.S. has ever built. But the system that justifies that number isn't the stealth coating or the speed. It's a sensor fusion processor the pilot never consciously operates. It just decides what they see. Going supersonic is the most detectable thing a fighter can do. Every generation of combat aircraft before the F-22 accepted that as an unavoidable cost. You needed the speed, so you lit the afterburner, and the instant you did, you broadcast your position to every infrared sensor within range. The F-22 was designed to break that trade-off entirely. The afterburner operates by injecting raw fuel directly into the exhaust stream behind the turbine and igniting it. The result is a sustained column of burning gas extending dozens of feet aft of the nozzle. At altitude, an afterburner plume generates an infrared signature detectable by IR-guided systems at ranges exceeding 50 miles, roughly the driving distance across a major metropolitan area from one outer suburb to the opposite edge. In a beyond visual range engagement, 50 miles represents several minutes of flight time and enough warning for a threat aircraft to maneuver, deploy countermeasures, and launch its own weapon before the attacking fighter reaches its employment zone. Afterburner is also a tactical liability that happens to produce useful thrust. A threat aircraft detecting that signature at 50 miles has time to act. Every fourth-generation fighter pilot managed afterburner use as a discipline: short burns, throttle back, except the slower acceleration in exchange for not being visible. The F-22 was built to remove that trade-off from the equation entirely. The Pratt & Whitney F119-PW-100 engines address this through thermodynamic engineering applied to one specific goal. Each engine produces approximately 26,000 pounds of thrust on military power. Dry, no afterburner. That figure is equivalent to the combined pulling force of 17 fully loaded diesel locomotives. Two engines produce 52,000 pounds of sustained dry thrust, applied to an airframe weighing 83,500 pounds at combat load. The numbers produce Supercruise, sustained supersonic flight without afterburner. The F-22 reaches and holds approximately Mach 1.5 on military power alone, around 1,100 miles per hour, fast enough to cross the distance from Washington to Philadelphia in under 4 minutes. The 50-mile IR detection window that afterburner creates never opens during the approach to the weapons employment zone. The F-22 has a thrust-to-weight ratio exceeding 1.0 at combat load on dry power. Most fighters achieve this only with afterburner engaged. The F-22 achieves it without. This ratio matters because transonic drag rise, the drag spike that occurs near the speed of sound, is what stops most fighters from going supersonic on dry thrust. The F-119 overcomes it with military power alone. It is the only production fighter engine in the current U.S. inventory that was specifically built to do this. But dry thrust alone does not explain why Supercruise matters. The explanation is what afterburner does to an aircraft trying not to be seen. The F-119's bypass ratio sits lower than most commercial turbofans, which trades fuel economy for high specific thrust output. Too high a bypass ratio and dry thrust falls below the Supercruise threshold. The aircraft reaches Mach 0.9 on military power and stops accelerating, which means the afterburner comes on and the IR signature returns. Too low and the engine achieves supercruise, but burns fuel at a rate that cuts unrefueled range below operational requirements, making the mission dependent on a tanker that may not exist in a contested environment. The F-119 sits precisely in the ratio that satisfies both constraints. The engineering program that produced it ran for over a decade before both numbers were met simultaneously. The throttles sit at military power. The aircraft accelerates toward Mach 1. There is no kick, no ignition event, no change in cockpit sound that marks the transition. The airspeed indicator ticks past 1.0 and continues climbing. The engines are running at the top of their dry output. The exhaust temperature sits well below afterburner ignition threshold. Every sensor on every threat system within 50 miles is receiving nothing from this aircraft that it was not already receiving at Mach 0.9. The aircraft is supersonic. The afterburner has not been touched. Every pilot who flew a fourth-generation fighter through a supersonic dash waited for the afterburner to kick. Here, there is nothing to wait for. And Supercruise is only half the stealth equation. The other half is where the weapons live. An F-22 carrying AIM-120 missiles on underwing pylons at Mach 1.5 is not a stealth aircraft. External stores at those speeds increase radar cross-section across every frequency band, create aerodynamic interference that degrades the low observable surface geometry on every adjacent panel, and generate drag sufficient to drop the aircraft below Supercruise threshold within minutes. External stores and Supercruise are mutually exclusive at combat loads. The solution is total internal carriage. The F-22 carries all weapons in 3 internal bays, one on each side of the fuselage for AIM-9 short-range missiles, and a centerline bay for AIM-120 beyond visual range missiles. At Supercruise speed, the aircraft is aerodynamically clean. The aircraft arrives at the weapons employment zone exactly as designed, fast, undetected, and carrying a tactical advantage the threat has had no opportunity to respond to. The centerline bay door weighs roughly as much as the hood of a full-size pickup truck. At subsonic speeds, the hinge assembly absorbs that load without difficulty. At Supercruise, the aerodynamic forces during operation are calculated for every airspeed in the flight envelope. Too heavy a door and the hinge assembly requires structural reinforcement that adds weight penalties through the adjacent fuselage frame. Too light and the door flexes under aerodynamic pressure at high speed, opening gaps along its sealed edges that interrupt the surface geometry the low observable design requires. The centerline bay's internal volume is roughly equivalent to the cargo space of a compact sedan trunk. Precisely sized, no excess, built for a specific set of weapons and nothing else. It costs $143 million per aircraft to keep those weapons inside rather than hanging them externally on pylons. That is not a design luxury. It is the operating requirement that makes everything else in this mission possible. But none of that matters if the aircraft's own surface geometry broadcasts its position regardless of what the engines are doing. But Supercruise only matters if the aircraft is actually hard to find. And stealth is not a switch. It is a geometry problem. Radar cross-section is not a fixed number. It changes with frequency band, aspect angle, and surface condition, sometimes by several orders of magnitude between one configuration and the next. The F-22 is specifically shaped to defeat X-band and Q-band radar, the fire control frequencies used by the most lethal threat systems in the current inventory. Against these frequencies, the aircraft's radar return is extremely small. Against VHF band long-range early warning radars, the aircraft has a measurably higher return. The physics of longer wavelengths interact with aircraft geometry differently, and no practical coding fully absorbs them at those frequencies. The aircraft does not advertise this. The operators of VHF early warning systems are aware of it. The F-22's approach to this problem is speed. It passes through VHF coverage quickly enough that useful targeting data cannot be developed before the aircraft is gone. The distinction matters operationally. X-band fire control radar guides missiles in their terminal phase. Defeating it means a weapon cannot reliably update its solution in the engagement's final seconds. VHF early warning radar provides the initial vector for intercept. Defeating VHF at the F-22's size would require a coding that does not yet exist. The aircraft accepts that vulnerability and addresses it with speed and mission planning. The surface geometry that defeats X-band works through edge alignment. Every panel edge on the F-22's skin is aligned to one of 2 prescribed angles. No edge runs in a random direction. This concentrates reflected radar energy into 2 specific directions, neither of which points back toward the threat emitter. A panel edge misaligned by more than a few millimeters, roughly the thickness of 3 stacked credit cards, creates a specular return that scatters energy in an uncontrolled direction. At X-band frequencies, That return can be detected at ranges that collapse the engagement timeline from minutes to seconds. The maintenance requirement is exact. A crew chief finding a panel edge out of tolerance does not mark it for the next maintenance cycle. The aircraft does not fly until it is corrected. The coating is not what holds the radar signature down. It helps, but the geometry does the real work. The radar-absorbent material on the F-22's surface is applied in layers thinner than a coat of paint and covers every exterior surface. Before every sortie, crew chiefs inspect each inch under controlled lighting conditions. The inspection happens before fuel, before weapons, before any discussion of mission readiness. The crew chief runs a gloved hand along the forward leading edge. The flashlight catches a chip near a panel seam, roughly the size of a thumbnail. Documentation begins immediately. The repair compound is mixed on site. Its working time is measured in minutes before it begins to cure, and temperature at the application point determines whether adhesion will hold under flight loads. Too thick an application and the compound creates a surface irregularity that scatters radar energy in unpredictable directions, producing a return larger than the original damage. Too thin and the absorption layer is insufficient. X-band energy reaches the metallic substrate beneath, reflects, and returns to the threat emitter as a coherent signal. The compound is applied and allowed to cure. Then it is sanded flush with tools calibrated to remove material in increments smaller than a human hair. This happens before every sortie. It is not considered extraordinary, it is the baseline. Every surface imperfection is a broadcast. And the aircraft lands with dozens of them after every flight. Bird strikes, hail, and abrasive rain at high speed damage the coating during routine operations. The F-22 absorbs these inputs and continues operating. The radar cross-section consequences are accounted for and repaired on the ground before the next sortie. The repair cycle means the aircraft's low observable status is never assumed. It is earned before each mission and verified before the first engine starts. The ground crew knows which surfaces took the most damage during the previous sortie. Leading edges, engine inlets, and wing roots accumulate the most debris impact at supersonic speeds. Rain at Mach 0.9 produces more coating damage than dry air at the same speed. The aircraft's low observable maintenance log tracks every repair location, every compound batch, every inspection result. If the same location shows repeated damage, the cause is investigated. Sometimes it is the environment. Sometimes it is a structural panel fit issue that pulls the aircraft from the flight line entirely. The F-22's nozzles can deflect plus or minus 20 degrees in pitch, an angle roughly equivalent to the slope of a steep ski run, enabling the aircraft to sustain controlled flight at angles of attack that would produce departure in any conventional fighter. This is thrust vectoring. At 60 degrees angle of attack, the wing is producing almost no lift and enormous drag. The nozzles deflect to maintain heading control, while the flight control computers make corrections at rates exceeding 1,000 per second. The vibration in this regime is unlike anything in normal flight, the airframe shaking at frequencies that transmit through the seat and the rudder pedals simultaneously. The pilot's inputs are marginal. The computers are flying the aircraft. Too aggressive a nozzle deflection at high angle of attack and the flight control system cannot compensate fast enough. The aircraft departs controlled flight. Too conservative, and the maneuver fails to produce the required heading change. The energy state collapses, and the aircraft becomes a slow-moving target at an altitude where slow-moving is a death sentence. The system that makes the F-22 nearly impossible to engage in close combat also adds mechanical complexity that a conventional fixed-nozzle fighter never encounters. Every post-stall sortie cycles the vector actuators through load ranges they were designed for but still wear from. The nozzle deflection mechanism on each engine weighs more than a loaded motorcycle. It responds to flight control inputs measured in milliseconds. It has never produced a fleet-wide failure. It has produced maintenance requirements that would not exist without it. The F-22 carries more sensors than any fighter ever built. The pilot sees none of their individual outputs directly. But all of that geometry and engine design leads to a single moment, when the pilot decides to act on what the sensors are showing. and the sensors are showing things the pilot's eyes never could. The ALR-94 passive detection system can detect and classify a threat radar emitter at ranges exceeding 100 miles, using only the emissions the threat system itself produces. The F-22's own radar does not need to be active for this. While the aircraft is supercruising in, electromagnetically silent, the ALR-94 is building a picture of every radar system operating in the threat environment. It identifies emitter type, bearing, and in many cases, mode, whether the threat system is in search, track, or fire control mode. By the time the F-22 reaches its planned engagement range, the passive receiver has often provided enough information for the pilot to understand the full tactical environment without having broadcast the aircraft's own position once. The AN/APG-77 radar uses a low probability of intercept waveform, a transmission technique that spreads the radar's energy across a wide range of frequencies and timing intervals, making it extremely difficult for a threat receiver to identify the signal as a coherent radar emission. Standard radar warning receivers detect radars by recognizing patterns in the incoming signal. The APG-77's LPI waveform does not produce recognizable patterns. The threat aircraft's warning system may register increased electromagnetic noise. It will not register a classified radar track. The F-22 can be acquiring a weapons quality solution on the target while the target's crew believes they have not been detected. The APG-77 can detect a target at ranges approaching 100 miles under appropriate conditions. The ALR-94 passive system can detect that same target's own radar emissions at ranges greater than that, often significantly greater. The sequence this creates is operationally decisive. The F-22 knows a threat is present before it uses its own radar, and when it does use its radar, the threat may not know it is being painted. The sensor fusion processor combines these inputs: passive detections from the ALR-94, active radar returns from the APG-77, data link contacts from other aircraft, into a single tactical display. The pilot sees tracks, not sensor outputs. The display shows a contact at a bearing and range with a confidence rating and threat classification. The pilot does not know whether that contact was detected by the radar, the passive receiver, or a combination of both. The aircraft decided. The pilot acts on the result. In every prior fighter, the pilot managed sensors individually. In the F-22, the sensors manage themselves and deliver a conclusion. The pilot's thumb moves the radar to active. The APG-77 transmits its LPI waveform. The threat aircraft's radar warning receiver registers increased background noise, not a structured threat signal. The F-22's display refines the track to weapons quality. The pilot looks toward the contact on the main screen, the HMCS reticle. The cue, projected onto the helmet visor, moves to align with where the pilot is looking. A glance is enough to cue the weapon. The targeting geometry is already inside the AIM-120's kinematic envelope. The solution has been valid for more than a minute. The APG-77 detection range of roughly 100 miles is approximately the distance from Philadelphia to New York City as the aircraft flies. The ALR-94 detected the threat's radar emissions from well beyond that. Too early a radar activation and the threat detects the emission, begins defensive maneuvering, and the engagement geometry changes before the missile reaches terminal phase. Too late and the engagement closes to within visual range, the BVR advantage evaporates and the fight becomes a turning engagement that neither pilot originally planned for. The missile leaves the aircraft before the pilot consciously completes the decision sequence. The AIM-120 sits in the centerline internal bay on a pneumatic launcher. At Mach 1.5, relative airflow outside the bay exceeds 600 miles per hour. The launcher ejects the weapon downward and forward, away from the bay structure, at a velocity calibrated precisely for this airspeed. Too little ejection force and the weapon contacts the bay edge as the aircraft passes over it. Contact at those speeds is not a handling problem, it is a detonation risk. Too much, and the weapon tumbles in the initial airstream, the fins unable to stabilize the body before the guidance system falls outside its correction envelope. The margin between those outcomes is fixed for each weapon type and not adjustable by the crew. The bay door opens at Mach 1.5. The airframe shutters immediately, a low resonant vibration that transmits through the seat and the instrument panel simultaneously. Airflow noise in the cockpit doubles. The pneumatic ejector fires. The weapon clears the bay. The door closes 3 seconds after it opened. The vibration stops. The radar cross-section returns to baseline. The aircraft is a low observable platform again. The AIM-120's motor ignites approximately 150 feet from the bay. The distance the missile travels in the fraction of a second between ejection and ignition, separating the exhaust plume from the F-22's engine inlets and the aircraft's own IR signature. 150 feet at Mach 1.5 takes less than a tenth of a second. The separation exists because without it, the motor exhaust plume would affect the aircraft. The engineers calculated the required distance. The launcher provides it automatically. The F-22 is already turning away. The throttles return to military power. The afterburner, if used during the dash, goes cold. The IR signature begins collapsing. The radar returns to LPI mode. The aircraft's electromagnetic and infrared profile is returning to the baseline it maintained during ingress. The threat track continues to update via the ALR-94 passive receiver. The pilot is watching a track, not looking for an aircraft. The mission computer has recorded the time of release, the aircraft's airspeed, altitude, and heading at the moment the weapon left the bay. Every parameter that could affect accuracy is logged automatically. If the weapon misses, the data identifies which variable was outside tolerance. If it hits, the same numbers are archived as a reference standard. The aircraft kept the record. The missile reaches terminal phase. The guidance system makes its final correction and updates. The threat track stops updating. The F-22 is already gone. 2 is already gone. 2 is already gone.